Hey guys, today we are taking a look at our notes for 3.3, which is all about solving inequality systems. So, a system of inequalities is just a set of two or more inequalities that use the exact same variables. So just like with our systems of equations that we looked at earlier in the chapter, our systems of inequalities are just multiple different inequalities that use the exact same variables. So with those, if we're looking for identifying solutions to our inequalities, it is still the same general definition. It is still values that make my inequalities true, but obviously with it being a system, we need to make sure that it's an x and y value or a variable value that makes all of my inequalities true. So I can't just be a solution to one of my inequalities, I have to be a solution to both of my inequalities or all of my inequalities. So if we're checking to see whether or not something is a solution, if we're doing it algebraically, that is just going to be plugging in my x and y values into my inequalities to check to see, does it make both of them true? If it makes both of them true, then it is a solution to the system. If it does not make both of those inequalities true, then it's not a solution. So for this first one, example number 1, we're checking to see whether or not 4, 2 is a solution to the system. So I'm going to start with this top one. So if I plug in 4 for my x value, and 2 for the y value, it's supposed to be greater than -2. And of course we end up with 6, which is greater than -2, so it is a solution. So far so good. 6 is greater than -2, so it's a solution to my top inequality. Down below, I'll do this in green, but here if I plug in 4 for my x value and 2 for my y value, I'm supposed to end up with 4 minus 2 is greater than or equal to +4, which means 2 is greater than or equal to +4, which is not true. So since it is not a solution to both of my inequalities, it is not a solution. Solution, there we go. So if it made both of them true, yes, it is a solution. If it doesn't make both of them true, regardless of whether one of them is or isn't, it's not a solution to the system. Okay, the other way that we can do this, the other way we can identify solutions, is by graphing them. So solving a system of inequalities by graphing is going to require us to have some dotted versus solid lines and shading above versus below. Now before we get into this, I do want to give you a little organizer that I like to refer back to when we're talking about the shading of our boundaries, because there are two different ways of shading. Right, we looked at this back when we graphed just a regular two variable inequalities. We had shading above versus below, and then either having our boundaries be solid or dotted, depending on whether or not we had or equal to's. Right, so remember, if we had this inequality, or we've got this, here we go. So all of this first column, if it's less than or equal to, we are shading below. If it is greater than or equal to, we are shading above. When it doesn't have an or equal to, that was a dotted boundary. When it had the or equal to, it was a solid boundary. Now remember, all of these assume y is by itself and on the left side. So that would mean we would have to have it as y is less than, y is greater than, y is greater than or equal to, y is less than or equal to. Right? It has to be y by itself. If we don't use that method, that's where we have to go with the test point method, where we pick out a point from one side or the other of that boundary and check to see whether it's a solution or not. But we want to primarily focus on using this method, especially because it being a system of inequalities, we are going to need to graph multiple systems, and like keeping track of those test points and where it's true and not true gets to be a lot more complicated. So if we take a look at example number 2, we're asked to solve the following systems by graphing. So we're just going to graph each of these two different inequalities and figure out where those overlap. All right, so in this top one, I'm going to do my bottom one in blue. I'll do my top one in green. So my top inequality is y is greater than -2x plus 4. So of course, that is a y-intercept of 4. So up 1, 2, 3, 4. And I'm going to plot that y-intercept. It has a slope of -2, so down 2 and to the right 1. And once you have your boundary set up, or your two lines set up, you can go ahead and graph your boundary. So I'm just going to grab my ruler and get it lined up here. Now when I graph this, because it is just greater than, I'm going to do a dotted line for the boundary. So I'm going to connect my dots with a nice dotted line. There we go. I'm going to plot that y-intercept. And I'm going to plot that y-intercept. It has a slope of -2, so down 2 and to the right 1. And once you have your boundary set up, or your two lines set up, you can go ahead and graph your boundary. So I'm just going to grab my ruler and get it lined up here. Now when I graph this, because it is just greater than, I'm going to do a dotted line for the boundary. So I'm going to connect my dots with a nice dotted line. and do the best I can for that, right? That is my dotted line. That's good enough for me. If you want to use a different method or, try and be a little bit more clear with your dotted versus solid, that would be great. I'm just trying to use a wooden ruler on my computer screen, so bear with me. Okay, now before I move on, I do also need to shade this, right? I need to indicate which side of my solution, my boundary, do my solutions live. So in this case, because it is greater than, I'm going to be shading above my boundary, right? And above, in this case, if you're not certain, I always defer to the y-intercept. So my y-intercept above points up from where I'm going. So I know that everywhere above my graph is going to be shaded above. So I'm going to go ahead and just shade this in green, and then we're good to go. Now I'm going to repeat that process with my bottom inequality. My bottom one was y is less than or equal to x minus 2. So that would be a y-intercept of negative 2. The slope is positive 1. So up 1, right 1. So now that I have my y-intercept and my slope plotted, I can go ahead and connect those dots with a nice straight line. And again, because it is or equal to, it's going to be a solid boundary. Okay, so now that I have my line set up for my boundary, it is less than, so I'm going to be shading underneath my boundary. So shading underneath going to be all of this area here. Now, since we are looking for where those shading parts intersect each other, right, that would be kind of the same thing as where my graphs intersected for a two-variable system of equations. I'm looking for where am I shading for both of my two boundaries. So because I use two different colors, I can see kind of in this area over here, my blue and my green mixed together would be my solution set. So you can highlight that if you want to. As long as I can tell when I'm grading this that it is shaded for both, I don't care how you go about doing that. So some people like to just shade where it's overlapping, like to just wait and see, okay, I'm supposed to be above the green line but below my blue one, and they'll just shade in like I have it highlighted here in yellow. Some people like to do what's called cross-hatching, so they'll shade kind of diagonally in one direction for one of my boundaries, shade diagonally in the other direction for my other boundary, and you can kind of see it kind of darkens in. Or people like to mix different colors together. Maybe you graph one in red and one in blue, so then where it's purple is my overlapping. It is really up to you. As long as I can tell where both of them are supposed to be shaded versus one or the other, then that is fine. I just need to make sure that I can see where does that happen. Okay. So for my next inequality system, for number 3, we've got y is greater than 1/2 x plus 1. My bottom inequality is y is less than 1/2 x minus 3. So I'm going to do the same thing. I'm going to do my top inequality in green. So positive 1 is my y-intercept. I am up 1 over 2 for my boundary. And I'm going to go ahead and I'm going to do it a little bit nicer for us to make sure we can get a nice clean boundary. Now this was supposed to be a dotted line, so I'm going to go ahead and erase a couple of points in here just to make it dotted again, because my ruler functionality is still not wanting to agree with me on the computer here. So I am dotted in that regard. My original inequality was greater than for that top one, so that tells me I'm going to be shading above. So again, I'm going to do this, the kind of the cross-hatching style I was just referencing. So this would be the method that you would want to do if you're just going to use one color. I know there's a handful of us that have all of our beautiful writing utensils and love to color code everything, and that's fantastic and love that for you guys. But for those of us who are just pencil person, or the handful of us that are just a single color pen person, then just make sure you've got that structure in place as well to be able to handle it. So I'm kind of diagonally shading just one direction for this first one, and then when I graph my second one, I'll go diagonally the other direction, so it kind of creates these little X's everywhere where it's overlapping. All right, so going to my bottom one in blue, my original bottom inequality was y is less than 1/2 x minus 3. So that is a y-intercept of negative 1, 2, 3. And then 1/2 is my slope, so up 1 over 2, up 1 over 2. There we go. Doesn't take very long to get some extra points here lined up, and then I can kind of just do my arrows on the end, and we're in good shape. Now these ones are parallel to each other, so how this ends up getting shaded is going to tell us whether or not we have anything that's overlapping or if it's one of our special cases. Now, because this was a less than originally, I'm going to be shading underneath, right? Less than is underneath my boundary. So this is how I would shade regardless of how they'd overlap each other. So you can see like I'm going diagonally crosshatch from one direction, crosshatching the other way. So then if there was overlapping, they would create these kind of tiny little X's. But in this one, we don't have anywhere where my graph overlaps each other, right? We're above my top boundary, we're below my bottom boundary, and more importantly, they're parallel to each other. Right? We could have noticed that and probably did from the get-go. Both of my inequalities had 1/2 as their slope, so I knew they're going to be parallel to each other. But just knowing that doesn't guarantee it's going to be a special case. Because if both of them were greater than problems, or even greater than or equal to's, we would have overlapping because I would be shading above my lower boundary and my top boundary, so then they would overlap above that top one. So you just have to graph them and then wait until the end to make your conclusion. But here, since my shaded areas don't overlap at all, it is no solution. That is still possible. We do still have those special cases. We could have infinitely many solutions, but that would have to be where like they're coinciding lines and shading the same direction. All right, so that's most of our problems. They're just giving us two inequalities. We graph the two of them, shade them, dotted versus solid for our boundaries, and figure out where they overlap. We do have this other type of problem that really is going to set us up for 3.4 when we're talking about what's called linear programming, where we have a 3 inequality system. And what they're asking us to find in this case is to find the coordinates of the vertices of the figure formed by the system. So what that means is that when I graph my 3 inequalities, they're going to interact with each other to create a shape. Obviously with 3 lines, it's going to be a triangle, but how that triangle looks, how they interact with each other varies from problem to problem. And what they're asking us to find is the coordinates of the vertices of where they intersect, so that shape that is formed by my intersections of my shaded areas, I'm trying to find just what are the coordinates of the corners, right? That's what vertices are, of that shape. Okay, so if we take a look at each of these 3, we're going to have to rearrange to put these into slope-intercept form in order for us to graph them. Or you could look at these in terms of like x-intercepts and y-intercepts. But that kind of negates our little like reminder Punnett square looking thing where above versus below, dotted versus solid, we can't use that unless y is by itself. So if I wanted to solve my inequalities to get it into intercept form, I'm going to do all 3 of them first. Okay, so in this top one, that's easy. I'm just subtracting x from both sides. This inequality becomes y is greater than or equal to negative x minus 1. So a slope of -1, a y-intercept of -1, easy peasy. My middle one in green, I'm going to start by subtracting x again, but that gives me a negative y is less than or equal to negative x plus 6. And I have to have it as just y by itself, not negative y. So in this, I'm going to also have to divide by -1 all the way through, which ends up giving me y. This becomes greater than or equal to x minus 6. So remember, if I multiply or divide by a negative in an inequality, it has to flip the direction of that inequality from a less than to a greater than, or vice versa. So that is my original bottom, my middle inequality, just rearranged into slope-intercept form. Okay, my bottom one in in red here, I'm going to start by subtracting x on both sides. That gives me 12y is less than or equal to negative x plus 32. And then I'll go through and divide by my 12 all the way through. So I end up with y is less than or equal to negative 1/12 x plus, what is that, 16 over 6. So an 8/3. 8/3 is my y-intercept. So that one's going to be kind of ugly. I might want to try and figure out something else to do for that, to be able to find a point that'll work out nicely for me. But we'll kind of see. Again, we're looking for where are those lines intersecting each other, so we can look at trying to find those vertices in some other ways as well. Okay, so if I go ahead and start graphing these, I've got y is greater than negative x minus 1 back in blue, so -1 for my y-intercept. And then my slope being -1 tells me down 1 over 1. So there we are. This is going to be a solid boundary because it was greater than or equal to. So I've got 1, 2, 3, 4 over here. Get that nice and straight. There we go. And I'm going to be above that boundary. Now, I'm going to wait in this case. I'm going to show you that the option on how we could graph where it's just waiting until the very end to see what that overlapping shape is. Now, I would put some reminders for myself. I know I want to be above that boundary. So I'm going to put just like some little arrows here just as a refresher or reminder for myself when I go to shade what part I'm shading relative to that blue line, especially because we've got 3 of them here. Okay, for my original middle one in blue, we've got x minus 6 with our equation, right? Y is greater than or equal to x minus 6. So 1, 2, 3, 4, 5, 6 is my y-intercept, is right here. And then positive 1 for the slope is up 1 over 1. So we are starting here and going all the way across. Make sure that's lined up nice and straight. Okay, we are greater than, again, right, greater than or equal to. So I'm going to be above this for my boundary. So far I'm kind of in the top half of that area. And now my last one, I have to graph where does like y equals, what was it, less than or, sorry, y is less than or equal to negative 1/12 x plus 8/3. So 8/3 we know is 2.6 repeated, right, 2 and 2/3. So we could approximate where that happens. So 1, 2, and 2/3 would be right about here. Oops, I forgot to switch to red. Let's do that. So 2 and 2/3. And then negative 1/12 for my slope is down 1 over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we're going to be way off my graph paper over here. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, down 1. And so we are right here. All right, so we're going to have to approximate where that looks in this graph because of the size of the graph paper that I have chosen. But we are going to be... Oops, why didn't my computer lock into a straight line? Let's undo that. Come on, there we go. So we're going to approximate where that is. Make sure it goes through both of my points. There we go. And because this was a less than or equal to, I know that I'm shading underneath this boundary. So we can see kind of where all those arrows are pointing is that feasible region. That is my intersection of all 3 of those inequalities. So I'm going to shade this in purple. So this is my area that is formed by the intersection of those things. All right, so now that I know where they intersect each other, I need to figure out what are the coordinates of those intersections. All right, so in this case, I have to find where, like, what are the corners of the triangle here, which would be right down here. Right, we've got this coordinate, we've got this coordinate, we've got this coordinate. Now, this is going to be really important for us to make sure that we know where that happens precisely. And because we had to approximate where that red graph was, we're going to have to use our calculator for this. Now, we showed you guys how to find those intersections before, so I'm going to go ahead and pause, get my calculator pulled up, get my equations typed in here, and then I will pick back up in just a second to kind of show you guys where that intersection happens. Okay, so now that I have my equations typed in, now I'm going to do this just because I only care about finding the intersection between them. I'm not going to concern myself with changing these equals to match their inequalities to shade it. Your calculator is capable of doing that if you want to, and if you really want that instruction on how to make that look, we can like schedule some time and figure that out once I'm back. But in terms of just finding these intersections, we just want to type them in exactly as is. Now, this is the other benefit of having it as y equals, or in this case, y inequality, is that we can just type these into our calculators when we want to find those intersections. So I've just got my 3 equations typed in here. Obviously, that bottom equation with the negative 1/12 for my slope and my 8/3 as my y-intercept is going to be the uglier one. There's ways of your calculator doing fractions for us, but it is just as effective to just put parentheses with fractions in there. Makes it more efficient for us. So once we have those equations in there, we can go ahead and graph. Now I've already done this just to make sure that it matched up correctly, and you can see my blue graph was that original top equation, my red graph was this original middle equation, and then my black one here, my darkest one, is my original kind of messy equation, my negative 1/12x plus 8/3. So if you want to figure out where they intersect each other, remember that would be second and then calc, which is the trace menu, and we can go down to here to number 5 to find out where they intersect. Now this is where it is going to be important for us to tell it which intersection we're looking for, because what it's going to intersect with is going to depend on where I'm looking, right? If I want to try and find this intersection between my left, my blue graph and the dark one, my black one, I'm going to go over here and say, hey, I think around here on my first curve is where they intersect each other. And then, whoop, nope, I messed up. Okay, so let's go ahead and do an intersection. All right, so it auto-corrected me. I didn't catch that on the second one where it asked me for what is the intersection of my second curve. That it kind of defaulted to the red one, and it said, oh, hey, by the way, this is the intersection between that red and that blue graph. So you can kind of see where my little cursor went right here on my screen to 2.5 comma negative 3.5 is the intersection between those two equations. Okay. Now, what I had meant to do, just because I clicked too quickly, I'm going to do the same thing over again. But I'm going to remember that positive 2.5 and negative 3.5 is one of my intersections, right? That'll be one of my solutions. In fact, I'll even go back over here now just to write that down to make sure I don't forget. One of my intersections was 2.5 comma negative 3.5, right? That is one of our vertices. And now I can head back over to my calculator. So I'm going to go back to the same thing, second calc on that trace menu, hit number 5 to find the intersection. But now again, I'm going to go back over here to my first curve. Sorry about all the click noises. We're going over here to as close as possible on my first curve. Go ahead and click enter. Now if you want to go to your other curve, obviously here it says second, and in my calculator it shows the red coordinates. If you click up, it goes to, like the colors on mine match which equation I'm dealing with. If your screen is not in color, you'll notice the top of my screen shows me which inequality or which equation I'm dealing with. So I want to go back to now find where my blue and my black one, my equation 3, intersect each other. So now I've jumped all the way up there. You can click enter and take a guess, and it gives you that negative 4 comma 3 is that intersection. So negative 4 comma 3 is my second intersection point. And now I'll go back and repeat the process again. Second calc, hit number 5. Now I want my first curve to be this black one, and I'm going to scroll all the way over here to try and find where my black and my red intersect each other. So we can go ahead and just keep scrolling. Now you don't have to be precise with this. You can absolutely just kind of spam and make sure that it's on the first curve. I go to my second curve to my equation 2, which was my red one, and it'll go, oh, hey, butthead, it's not there. It's actually all the way over here. But as long as you're guessing and telling it which curve and which other one to go to, it'll correct itself. And in this case, 8 comma 2 is that final solution. So over here, 8 comma 2 is my final answer, which if I look at my intersection points, and I was not precise with that, in my picture here, this red equation, my negative 1/12x, and all that stuff, like that does not match up perfectly, but it's because I was approximating where 8/3 was as a y-intercept. I was also approximating my negative 1/12 for my slope, but it at least makes sense. Negative 4 up 3 is about where those lines are, where they intersect on the top left corner. Positive 8, positive 2 is around where I have for my intersection. And then the one that should match exactly, 2.5 comma negative 3.5, where my red and my green and my blue intersect each other, that I've got circled down here in the bottom corner, that is exactly where they intersect. And that makes sense because those are the ones that I did not approximate. I was precise with those, but it is good that I used my calculator anyway, because I don't know for sure if that is actually negative 3.5, or negative 3.6. That is kind of the double-edged sword of graphing. It is usually easier to see those solutions, but more challenging to be able to find the intersections. So that really sets us up for what we're doing in 3.4 tomorrow. 3.4 is something called linear programming, where we're going to be kind of taking multiple different aspects of a problem and trying to find that feasible region to try and maximize and minimize some different values. So a little preview for what's coming up moving forward. But for right now, for just systems of inequalities, here is your homework. It is on pages 125 through 127. You guys are just taking a look at numbers 3 through 37, just odds. As always, if you guys have any questions, concerns, or anything like that, feel free to reach out. Make sure you guys are advocating for some help. And I will see you guys soon. Have a great day.